So our last speaker of this afternoon session is Daniel Greenberger. So take it away.
Okay, and I hope to convince you that everything I say is unconventional, and I start by using this old dinosaur-type presentation. Now, what I'm going to talk to you about is, it's my own approach to, I wouldn't say quantum gravity, but I would say the problems that are involved in quantum gravity. And my own feeling has always been that the reason we can't quantize gravity is because we don't understand some of the very basic concepts that go into quantum gravity. And one of the things that's bothered me since I was a student is that the very idea of mass is somehow, it's wrong. It must be wrong. And that's because it comes in as a passive parameter. And both in Newton's laws and in the Schrodinger equation, and even the relativistic equations, the mass is just there as just that, a passive parameter. On the other hand, the role it plays in physics is extremely dynamic. And for example, you take a proton and an electron and you bring them together and you get an H atom. And the mass of the H atom is not the mass of the proton or the electron. It's changed. Now, our formalism lets the energy change, but it doesn't change the mass. You can put it in by hand, but it seems to me there ought to be some nice interaction that automatically changes the mass in the same way as in the Schrodinger equation, the energy gets changed. And it ought to come in at the very beginning, even in non-relativistic physics. And so I think there's something wrong in the way we treat the mass. Now, relativistically, for example, you say E equals mc squared, but I'm sorry, you say E squared equals P squared plus M squared, C is 1 here always. Then E is a dynamical variable. P is a dynamical variable. And M, which comes in, is nothing but just a passive parameter. And yet, you know, if you take a hydrogen atom and you take two of them together, they get attracted. The mass of each of those is the mass of the hydrogen atom. That has nothing to do with the original proton or electron. And the same thing is gravitational. The gravitational mass of the hydrogen atom is the mass of is m sub h, and excuse me. And that should automatically be in there. It should come out, it seems to me, very, very simply. Now, there's a very nice argument due to Einstein, which on the real meaning of E equals mc squared. And usually in the textbooks, they tell you it's a bookkeeping device for adding up all the masses. But the real meaning of E equals mc squared is given by this lovely problem that he talks about, which is, imagine that you have a particle and it's at rest, and two photons come and hit it and get absorbed. And so you say that the energy goes up because the two photons get absorbed. But now if you go into a moving system, so call that S, if you go into a system S prime, where the particle is moving, at constant speed, and these two photons hit it. Once they get absorbed, it's still going at the same speed v, because it was at rest after it absorbed the two photons. But in this case, what happens is the photons are moving at an angle. And so not only does the particle absorb the energy of the photons, but in this case, they have some x momentum. So it absorbs the x momentum of the photons. So it picks up extra momentum. So here's a situation where the particle picks up momentum from the photons, but it doesn't change its velocity. And so Einstein says, well, clearly then it must change its mass. And so that's a very beautiful argument. But also what it shows is that what looks like energy in the rest system, in the moving system looks like mass, inertial mass. And so inertial mass and energy are really just two different aspects of the same thing. And that's needed for the Lorentz invariance of the system. Now, so if E and M are just different aspects of the same thing, how can one be an operator and the other just an idle parameter? And if there's any system, though, that can change its mass, shows that the mass must be an operator. So it seems to me that it's just not consistent to say that the mass should enter as a simple parameter. Now let's look at the equivalence principle. And Einstein said, when I realized that a particle in free fall doesn't feel any gravitational force, it was the happiest moment of my professional life. And one of my feelings is that we really don't fully understand the equivalence principle. And so how are we going to quantize gravity when we really don't understand some of these very simple things? Now, the equivalence, this is the weak equivalence principle, and it implies that an accelerated system is equivalent to a gravitational field. When the weak equivalence says all particles fall with the same acceleration in an external gravitational field. And now the way I like to say it is that in any force field, a minor miracle occurs. And the minor miracle is that you only need one parameter to describe the motion of a particle, and that's its mass. Nature could have been a lot nastier. And on the other hand, in a gravitational, external gravitational field, a major miracle occurs. You don't need any parameters to describe the particle. All particles fall, all particles behave similarly. They all fall at the same rate. It's the environment then that determines the motion, and the mass itself is superfluous. In other words, in the equivalence principle, the mass just doesn't enter. Now, if you let the gravity field get weaker and weaker and weaker, you end up with a free particle. And so, for a free particle, it's also true then that the mass is irrelevant, okay? A free particle has no mass. That is, the mass is undefined. All free particles behave the same. You know, they either, if they're at rest, they stay at rest. If they're in uniform motion, they stay in uniform motion. The mass doesn't enter as a concept in that. Now, for Newton's second law and third law, you need the mass, but for the first law, you don't. So the first law is really much more connected to the equivalence principle than it is to the second law and the third law. And so it's only when a non-gravitational force is applied that the particle acquires a mass. Now, this is true classically, okay, but it's not true in quantum mechanics. So it's a very profound, as simple as it sounds, it's a very profound statement. It's not true in quantum. A free particle in quantum mechanics has a de Broglie wavelength. It has a Compton wavelength. It has a mass. So the mass is there right from the beginning. And in other ways you see it too. It's right. It's in the commutation rules, P and Q, and you need a mass for the momentum. Now, so this tells you there's a certain fundamental rift between quantum mechanics and classical physics, and it's due to the equivalence principle. And because, and I don't want to discuss it, but after all, if the mass is there quantum mechanically, if you go to the classical limit, what makes the mass disappear? And the answer is fairly subtle, and there's no time to go into it now, but it's an interesting question. But the point is that when we teach quantum mechanics, the quantum mechanical particle has a mass from the moment it's created. Now, actually, that cannot be right. It cannot be right, because it violates the fundamental tenets of quantum mechanics. And I'll explain, oops, am I getting in my own way? I'll explain how. Let's say you have a particle A, and it decays into two particles, or I should say B and C, and maybe there's a second mode of decay, and it can decay into D and E. So A decays, and you're standing here, and a particle flies by. Now, is it B, or is it C, or is it D, or is it E? And the answer is you can't know the answer to that until you make a measurement. And it's the measurement that tells you which particle it is. Now, did the particle have a definite mass before you made the measurement? Well, Bell's theorem tells you can't know the spin of a particle, let's say in an entangled state, until you measure it. And then the same must be true of the mass. Okay? The particle can't have a mass at the moment it's created, because that's EPR reasoning. And Bell's theorem tells you that that's not right. So the particle can't be said to have a, now yet in our field theories and so on, they're all created in such a way that each field has its own mass. And I think it needs to be updated. I think that there's something seriously wrong in the way we do field theory. Not that it doesn't work, but that it violates the fundamental principles of quantum mechanics, which should give you pause when you're using that as your starting point for getting a theory of gravity, or quantum gravity. How do we get around the dilemma? It's simple. The mass should be a quantum mechanical operator, so that the mass operating on the state produces an eigenvalue, a definite mass. A measurement, in other words, of the mass puts it into an eigenstate. And until then, it's in a superposition. And this reconciles the classical case, the quantum case, and Bell's theorem. And so that's the mass. Now let's look at the proper time. Now, classically, there's only one time, okay? In a Euclidean space, there's only one time, Newton's time, which is the absolute universal time. Now, in relativity, the proper time is determined geometrically. And d tau d tau is the square root of 1 minus v squared dt. And in general relativity, the same thing happens. It's determined geometrically, the proper time. But in fact, it's determined, the proper time is determined dynamically. The proper time, you need to know something about the physics of the problem before you can talk about the proper time. It can't just be determined geometrically. I'll give you an example, if you can see this. Here, in other words, let's say you have a beam splitter, and a particle goes into the beam splitter, and it comes out with velocity v1, and it's split. And the part that goes through the upper part, the beam A, okay, let's say you give it a non-gravitational force and accelerate it. And then after a period of time, you bring it back to the original velocity. Meanwhile, this goes through a different path where it stays at the original velocity. And they recombine them at time t2. Now look at, say, this beam at t2. It's a mixture of this beam and this beam. But we've arranged it so that they both have different proper times, different passage of proper times. And one of them was accelerated and so on, and that slows down the proper time. So when they come back and they get recombined, they have two different proper times. And they interfere, and they hit a screen. And the question is, and TA is different from TB. And my question to you is, what is the proper time of the recombined beam? I don't even know if that's ever been measured. But if the original, let's say the original particle is unstable, okay? When does it decay? What's its proper time? Is it the time of A, the time of B, or do they get recombined in some way and interfere? Do the two proper times interfere? And my answer is, you bet they must. They have to interfere. And that means you're going to get an interference pattern in proper time. That means the particles won't decay in a nice uniform manner, but that there will be a wiggle on the decay. So then the next question is, I don't know what's going on here. The next question, anyway, is if the mass is an operator or a dynamical variable, what is its conjugate variable? And if you look at a plane wave for a particle, say e to the I p dot r minus et, if you put in p as mv and so on, put it in terms of velocity, and e in terms, and say r equals vt, and you just put that in, you get psi equals e to the minus m tau. So that plane wave is just e to the minus m tau. It's just, in fact, it's just the Lagrangian for the free particle. And now p dot dr and e dot dt are adiabatic invariants, and it seems to me that m d tau should also be one. And therefore, m and tau should be conjugate variables. M as an operator should be h bar over I d tau. Now you say, how can that be? Where does tau come in to the system? Well, it turns out that the whole thing fits very nicely into the Hamiltonian formalism. To remind you, if x is the coordinate and p is the momentum, say for a harmonic oscillator as an example, then energy is p squared over 2m plus 1/2 omega square m omega square x square. So the equations of motion are x dot, which is the velocity, is the hdp, and that's p over m, which is v, and p dot is minus the hdx, okay, which is minus kx, the force. Now, I'm telling you now that m and tau are are also to be considered as dynamical variables. So x and tau are the coordinates, and p and m are the momenta. So along with the equation that x dot is the h dp and p dot is minus the h dx, you also get that tau dot is the h dm and m dot is minus the h d tau. And so you have a theory here where the masses can change. If all you need is that if h is a function of tau, I'll put it this way first. If the Hamiltonian is homogeneous in x, you'll have a free particle. If it's inhomogeneous and it depends on x, that's going to produce a force which changes the momentum. If h depends on tau, it's going to produce a force that changes the mass. So here you have a theory where the mass can change, even classically. And it's the most trivial case to show you how consistent it is. Just take a free particle where h is the square root of p squared plus m squared. Now, where does that Hamiltonian come from? Well, just looking at the result. Now, x dot is v, is the h dp, and that's p squared over this, which is equal to v. The x dot is v. You can invert this and get p equals mv over the square root of 1 minus v squared, which is usual. But now we'll look at it this way. If tau dot is the h dm, it becomes m over the square root of p squared plus m squared, and that's equal to the square root of 1 minus v squared. So the equation d tau equals 1 minus v squared dt is, in fact, an equation of motion. Okay? It's not given to you geometrically. It's given to you by the form of the Hamiltonian, and it's dynamic. And if you put in a function of tau for h, okay, it's not only going to make the particle decay, but it's going to change the relationship of tau and t. So the formalism is all set up that it can it automatically handles these things. Now, I won't go through, this is the equivalence principle, but it's too complicated to go through in detail. But let me just say that if you have a particle, let's say in an external gravitational field, what happens is, as the particle accelerates, the proper time changes because there's going to be a difference in potential in the gravitational field. Well, if you have an unstable particle, okay, there still will be a change in potential. And if you have a stable particle and an unstable particle sitting right next to each other, okay, the unstable particle is not at rest in an inertial field. The stable particle is, but the unstable particle is not. It's accelerating. It's not accelerating in x. It's not moving. It's accelerating in proper time. So that a particle that is decaying is accelerating in proper time. There's and the same formula works as before, but 5 minutes? Good. Okay. So the same formula works as before, but you can make the potential depend on the proper time. And so here's a completely new role for gravity. It's no longer just the weaker sister of the other forces, okay, but when, see, in the usual case, phi, the potential depending on x and t, depends on, it tells you about the binding, or I should say the bending of space-time, whereas it also determines the scale of time for decaying particles, because if it depends directly on tau. And so here you have a system that completely, now let's see, there are many, many consequences of this. Let me just give you one or two in the time that's left. And here, for example, because they're conjugate variables, there has to be a uncertainty principle. In other words, if you want to measure the mass of a particle, you're going to mess up its proper time. And if you want to measure the proper time, it's going to have an effect on the mass. And here's a simple example to see that. And that is, imagine you want to measure the mass of some heavy particle, and by zooming a light particle around it and watching it scatter. Well, most of the effect will be in the region of closest approach, but what's going to happen is the heavy particle will bend the light particle, and it will give it a piece of X. And the bigger m, the bigger the piece of X it'll give it. So by measuring piece of X, you can measure the mass, okay? But at the same time, this light particle, as it goes by, is exerting a gravitational force on m. And as a result, it's going to affect its clock, the clock on m. And as a result, as it goes by, even if you knew the time exactly on m before you started, when this thing goes by, it's going to affect the clock. And that depends on the unknown distance of closest approach. So to the extent you don't know p sub x, you won't know m, and to the extent that you don't know b, the distance of closest approach, you won't know tau. And because delta p delta b is greater than h, it follows when you do the algebra that delta m delta tau is greater than h. It has to be, because they're both conjugate variables. You can always, in an experiment, change the parameters of the experiment slightly in such a way that that you can, instead of measuring one set of canonical variables, you're measuring a different. If you, instead of p and x, you can easily change it. You're measuring delta L delta phi or delta E delta T, and they all are consistent. You can't say that the uncertainty principle holds for some sets of canonical variables but not others, and by the same token, you can't say it doesn't hold for m and tau. Once you accept a dynamical role for these, there must be an uncertainty principle. And there are all kinds of other effects that you can work out, but where time is pretty much up, so I won't go into it. But at least I hope I convinced you that there are things that we really don't understand, even in elementary physics. And it seems to me that to try to quantize gravity without having a really good basic understanding of quantum mechanics, which goes all the way back to even the equivalence principle, is a fool's errand. And it's not, I shouldn't say a fool's errand. The people in the field are very bright. They're not fools. But if you start from the wrong place, and you may very well end up in the wrong place. And so my own hope is that nobody succeeds in in quantizing gravity to get to a quantum gravity, because if they do, if they get a theory that works, it will everybody will believe it, and they'll immediately get a Nobel Prize for it, even though nobody can measure it, anything. And on the other hand, I give you my personal guarantee that the theory must be wrong, and because it won't include some of the really basic things that have to be included. And I think that the ideas going back to mass and proper time have to go in from the beginning before you can quantize the system. And so that quantum mechanics is a very important part of it. To just quantize general relativity as such, I think, is just not the way to go. So anyway, that's the moral I wanted to give you. And so, thanks.
Thank you, Dan. So one question, then we could go straight to the discussion section. So yes.
So that has the mass problem has always bothered me as well since I was an undergraduate. But it seems to me that there's a much simpler solution. If you consider the mass, if you define the mass to be the magnitude of 4 momentum.
Of what?
4 momentum. So 4 momentum, the 4 momentum vector, then you don't have any of these problems, and you recover recover the metric and all of that stuff.
Well, let me answer that. The things I didn't say, unfortunately, is the mass has to be considered as the energy in the center of mass system of the particle, and and in order for this to be true, and the proper time has to be considered in the center of mass system. The proper time is a very different thing from the ordinary time, and because the proper time is of necessity is a dynamical variable, because it's non-local. It depends on the trajectory of the particle, and so you need to know something about the particle before you can talk about the proper time in the particle. It's not like the ordinary time at all. And there are mathematical factors, too, in it, so that things like the Pauli proof of that you can't quantize time doesn't work for the proper time. And so I think that what you say has a lot to it, and I started off working along those directions, but it's deeper than that, in my opinion. The problem is deeper than just that.
If you allow us, we'll continue to the discussion section very, very shortly. So let's thank Dan once again.